Hello students. So today I am explain about the equilibrium of a rigid body. Equilibrium of a rigid body. Now in laws of motion chapter you have learned about equilibrium of a particle. Equilibrium of a particle means what? A particle is said to be in equilibrium if the net force acting on the particle is zero. That is, total force acting on the particle is zero. That is the condition of equilibrium of a particle. Now here I will explain equilibrium of a rigid body. Now you know a rigid body may have two types of motions. One is translational motion, one is rotational motion. So translational motion is due to a force and rotational motion is due to a torque. So you can say that for total or mechanical equilibrium of a rigid body, what is the condition? The total force as well as total torque should be zero. Okay, so if total force and total torque acting on a body is zero, then the body is said to be what? In mechanical equilibrium or total equilibrium. Now total force zero implies what? It implies linear momentum equal to constant, and total torque implies what? As I have explained, it is angular momentum equal to what? Constant. So in other way you can say that a rigid body is said to be in total equilibrium if the linear momentum as well as the angular momentum is said to be constant. Okay, are constant. Then you have partial equilibrium. Now partial equilibrium means what? Here either the body is either in translational equilibrium but not in rotational equilibrium. That is, you can say that is translational equilibrium means what? Total force is equal to zero but total torque is not equal to zero. Then the body is called partial equilibrium. So let me give one example where total force is zero but total torque is not zero. So here you see, you take this example. If I open the mouth of the bottle, I will apply force this way, see. So this finger moves this direction and this finger moves along this direction. So they move in opposite directions. That means I am applying two equal and opposite forces. As a result of it, the total force is zero but total torque is not zero because it turns the body, it rotates the body. Torque is not zero. So here you can take the example. You see, suppose this is a body. Here I am applying a force in this direction, another force in the direction, exactly equal force. Okay, so they are at equal distance from the center. This is suppose R, this is also R. Okay, so this turns the body along this direction, it turns the body along this direction. Now in this case, if you find the total force, what is total force here? What is total force here? What is total force? F total is F minus F. Why? Because they are in opposite direction. Okay, but what is total torque here? Torque, you know, force into perpendicular distance. Now you see, both are in same direction. Both are what? Anti-clockwise directions. So torque is what? Force into perpendicular distance. So for this, the torque is F into R plus for this torque is F into R. So it is twice Fr. That means it is not equal to 0. That is not equal to 0. So this is called what? Partial equilibrium. Or you may take the case of what? The body is in rotational equilibrium equilibrium, but not in translational equilibrium. Okay, translational equilibrium. That is here torque will be 0, total torque will be 0, but total force is not 0. So this is called what? Partial equilibrium. Means body is either rotational equilibrium, not in translational, or translational equilibrium, not in rotational equilibrium. Okay, so this is called what? Partial equilibrium. Now move to your total energy, total kinetic energy of a rolling body. So as I have explained earlier, that rolling motion is nothing but combination of translational and rotational motion. Now suppose a body is rolling over the surface with a velocity v, linear velocity v, and angular velocity is omega. So here it executes both translational motion as well as what? Rotational motion. So total kinetic energy means what? It is the kinetic energy of translation plus kinetic energy of rotation. Now kinetic energy of translation means what? It is half m v square. And kinetic rotation means what? You know, half I omega square. I have given you the formula earlier. Here in place of mass, you write moment of inertia. In place of velocity, you write angular velocity. So this is the total kinetic energy of what? Kinetic energy of what? Rolling body. Okay. So here you can write like this also. Half m v square plus half I is moment of inertia. So I you can write. It is m k square. K is radius of gyration, okay? Into omega square. Or half m v square plus half m k square. Omega you can write v by r, okay? Because you know v is equal to r omega. So from here you can take common half m v square will be 1 plus k square by r square. Or simply you can write this is kinetic energy of translation 1 plus that is you can write r square plus k square. So this way also you can represent. Here k is what? Don't confuse this k and this k. Okay, this k is what? Radius of gyration. So this k is radius of gyration. Okay, radius of gyration. Okay. And this k is what? Total kinetic energy. Okay, this total kinetic energy. So this way also you can write the total kinetic energy of a rolling body. This kinetic energy of translation plus kinetic energy of rotation. Now let me derive a very important formula. That is velocity of a rolling body rolling down the inclined plane. Rolling down the inclined plane. Okay. So here this is suppose inclined plane. The inclined plane is h. This angle is theta here. Now this body suppose is rolling from this point. Okay. And this is the horizontal surface here. We will find the velocity when we reach this point. Now at the topmost point here, velocity is 0. Okay. At this point, so velocity is v. And this is suppose the length of the inclined plane, suppose s. Now here we will apply the law of conservation of energy. So here the body has only potential energy and here the body has kinetic energy. But it is rolling body, so both kinetic energy of translation as well as what? Rotation. So from conservation of energy, So here you have total kinetic energy is what? Half mv square plus half I omega square. That is kinetic energy of translation plus kinetic energy of rotation. Then is equal to what? Here at this point only potential energy mgh. So from here you can write it is mv square plus I omega square equal to 2 mgh. From here you have to find out v. Okay. So mv square plus I omega you can write v by r. Okay. Whole square 2 mgh. From here you can take common mv square. It will be 1 plus I v you take common mr square. Okay. mr square equal to 2 mgh. From here v square will be what? M cancel out. So 2gh by 1 plus I by mr square. So from here v you can write root over 2gh 1 plus I by mr square. So this is one of the very important formula. Okay, from this formula you will get questions in entrance. Okay, NEET as well as in JEE Mains. So here I is what? I is moment of inertia. I is moment of inertia. Okay, inertia. R is radius of the body. Radius of the body. Now of course m is mass. So here the velocity, what do you get? Velocity, this v is equal to what? Root over 2gh 1 plus I by mr square. So this we get. This is the velocity of the body rolling down the inclined plane. Root over 2g, h is the height of the inclined plane. Okay, 2g by root over 1 plus I by mr square. Now, what we have seen that the velocity of the body depends on what? It depends on moment of inertia. And how it depends? It depends, you see, inversely. So you can say that smaller the moment of inertia of a body, more is the velocity. So this is another important point. You can say that smaller is the moment of inertia of a body, greater will be the velocity on reaching the bottom of inclined plane. Okay, bottom of inclined plane. Okay, as we have seen that v is inverse to what? Moment of inertia. So here you can take example. Suppose a solid sphere, a hollow sphere and a disc having equal mass and radius are allowed to roll down an inclined plane which will reach the bottom earlier. Okay, so a solid sphere, a hollow sphere and a disc having same mass and radius are allowed to roll down an inclined plane which will reach the bottom earlier. So here you see, for solid sphere, what is the moment of inertia? You know, 2 by 5 mr square. For hollow sphere, what is the moment of inertia? 2 by 3 mr square. And for disc, what is the moment of inertia? It is half mr square. That already I have given. Okay. So here you see solid sphere has smaller value of moment of inertia. So we know smaller the value of moment of inertia, more is the velocity, and more is the velocity means what? It will reach earlier. So solid sphere will reach the bottom earlier because it will attain greater velocity. Okay. So this way you can answer it. Now let me find out acceleration of a body of a rolling body down the inclined plane. Down the inclined plane. Okay. So how can I find acceleration? Use this equation here. It is v square equal to, you can write e square plus 2as. So v square equal to, u means initial velocity, here it is 0. Okay. 2as. S how can you find out? You take here, you take sin theta. It is perpendicular hypotenuse, means h by s. So from here, what is s here? S will be h by sin theta. Okay. So this will be what? Then v square. You put the value v. This v is root over 2gh 1 plus I by m square. So what will be v square? It will be 2gh 1 plus I by m square. Okay. So this will be 2ah. It is sin theta. So from here h will be cancelled out. 2 cancel out. Sorry, 2ah here, or 2ah. A will be there. So it is g sin theta by 1 plus I by m r square is equal to a. So ultimately a will be what? G sin theta by 1 plus I by m r square. So this is the value of acceleration. So from here also you can say that acceleration is what? Inverse to moment of inertia. From here also you can say that smaller the value of moment of inertia, more is the acceleration. Okay, because it depends on what? Inverse to moment of inertia. So these are two very important formula. In exams you may get direct questions from here. Okay, acceleration of rolling body down the inclined plane or velocity of the rolling body. Similarly, you can find out time taken by the rolling body on reaching the bottom of inclined plane. Okay, inclined plane. That means from here to here, what is the time? Time you have to find out. So what we do? We use this equation here. That is s is equal to ut plus half at square. Okay. So s will be, u is 0 here, initial velocity is 0 here. It is half at square. So from here t will be root over 2s by a. You put the value of a already I have derived just before. That is a is what? It is g sin theta by 1 plus I by m r square. Okay. So this will be your root over 2s 1 plus I by m r square by g sin theta. Okay. So this is the value of our time. Here you see time that directly depends on moment of inertia. From here you can say that greater the value of moment of inertia, more is the time taken by the body on reaching the bottom of the inclined plane. Okay. So these three are very important formula you have to remember. Okay.